All right, 55. When 6-gram sample of sodium hydroxide dissolves in 100 grams of water in a coffee cup colorimeter, the temperature rises from 21.6 degrees Celsius to 37.8 degrees Celsius. Calculate the delta H for the solution process. Assume that the solution has the same specific heat as pure water. All right, so at this point in the course, we know what the specific heat of pure water is, right? It's 4.18 joules per gram per degree Celsius. So we need to know is how much solution we have. We need to know what the temperature change is, and we can figure out how much heat is being absorbed by the water, right? This is an exothermic reaction. So heat is leaving the system, right? Leaving this dissolving system, going into the water. How do I know this? Because the temperature went up. All right, so there's my beaker, my 100 grams of water. I'm putting in 6.5 grams of sodium hydroxide solid. It dissolves, and in the process, the temperature goes from 21.6 degrees Celsius up to 37.8 degrees Celsius. All right, so this is visually what's happening, right? You're dissolving sodium hydroxide. That's the system. The surroundings is the water. So how much does the water absorb the heat? So what I need to know is the total mass of the solution, right? So this problem is hard in that you had to remember that the 6 grams of sodium hydroxide adds to the thing that is absorbing the heat, the surroundings that's absorbing the heat. Of course, that didn't change the value of C, but we're going to overlook that. And the temperature change, right? They told me you went from 21.6 to 37.8. So when I plug this into Q is equal to NC delta T, I convert to joules. I want to convert this to kilojoules, right? It's just easier to look at, right? Instead of looking at 7,000 something joules, it's easier to look at 7.22 kilojoules. All right, so that's how much heat was absorbed by the water. What they wanted to know is what the delta H per mole of sodium hydroxide is. All right, so you dissolved a 6.5 gram sample. All right, so for every 6.5 grams, that's how much heat went into the water, the 7.22. So you divide by grams and we get kilojoules per gram. We want to use the molar mass of sodium hydroxide to go to moles, right? We weren't interested in joules per gram, we're interested in joules per mole, right? So put grams up the numerator, moles down the denominator. When I multiply across, grams cancels, and I end up with what the delta H is for the dissolving of 1 mole of sodium hydroxide. Again, the negative sign indicates that heat is leaving the system, the dissolving process. Chapter 5 can really be broken down into 2 sections, right? Using coffee cup colorimetry or bomb colorimetry to measure heat changes, or using Hess's law to calculate heat changes. So in problem 63, I'm using given thermochemical equations to try to manipulate them to come out with the equation that I want. I want the combustion of tetraphosphorus hexaoxide to form tetraphosphorus decaoxide. That's what I want. And I'm given the heats of formation of tetraphosphorus hexaoxide and tetraphosphorus decaoxide. So how can I manipulate these? When I add them together, I come out with the equation that I want. Whatever I do to the chemical equation, I have to do to the delta H. So this is what I'm given. All right, I'm given the heats of formation of these 2 things. So I notice I want to burn, right? I want to combust tetraphosphorus hexoxide. I want that going in as a reactant. So I'd have to turn the heat of formation of tetraphosphorus hexoxide around. So if I do that, I change the sign on delta H, right? If it's exothermic in one direction, it's endothermic in the other direction. All right, so now how does this work? It looks like that's all I had to do. Now when I add these 2 together, right, I want to end up with 2 oxygens at the end. I got 5 oxygens going in, 3 oxygens coming out. So when I add this together, I'm redundant on 3 of those oxygens, right? So 3 of those oxygens will cancel. phosphorus solid goes in, phosphorus solid comes out, they cancel, and I'm left with what I want. The tetraphosphorus hexoxide reacting with 2 moles of oxygen to make the product. So if I add the equations to get the overall equation, I add the delta H's together, and that'll give me the heat change. I mean, that's the amazing thing of Hess's law, right? I just have to add equations together to come out with the equation that I want, and I know what the heat change is without measuring. All right, in 64, I'm given the heat of formation of 2 moles of carbon monoxide and the heat of formation of 2 moles of methanol, and I want to turn it into a reaction between carbon monoxide and hydrogen to form methanol. All right, so all right, I want methanol going in, right? So I turn that around. So when I turn that around, I change the delta H from exothermic to endothermic, right? I change the sign. And I only want 1 mole of methanol coming out, right? So I'd have to divide the... I'm sorry, I only want 1 mole of I only want 1 mole of methanol coming out. I want 1 mole of carbon monoxide going in, and I want 2 moles of hydrogen going in. So I'd have to divide the top equation by 2 in order to get 1 mole of carbon monoxide going in. If I divide the equation by 2, I got to divide the delta H by 2. And I have to divide the second equation by 2 in order to get 1 mole of methanol coming out. So when I do that, I change the coefficients to this. So half a mole of oxygen going in, half a mole of oxygen going out. They'll cancel. 1 mole of carbon going in, 1 mole of carbon going out, that'll cancel, and I'm left with what I want. 1 mole of carbon monoxide reacting with 2 moles of hydrogen to make 1 mole of methanol. So whatever I do to the equations I did to the delta H's, and when I add them together, I get the overall heat change. Nice. For each of the following compounds, write the balanced thermochemical equation predicting the formation of 1 mole of compound. Right? So this is what the definition of delta H sub F naught is. Right? It's how much heat is released in the formation of these compounds from their elements. Elements, as we know, are treated as having a delta H of 0. So when looking at A, right, I want to form a mole of nitrogen dioxide. I'd have to react half a mole of nitrogen with a full mole of oxygen to make 1 mole of nitrogen dioxide. So 1 mole of nitrogen going in, right? That half a mole of N2 gives me 1 mole of nitrogen atoms going in, and reacting with 2 moles of oxygen atom to make 1 mole of nitrogen dioxide. So this is the definition of the heat of formation of nitrogen dioxide, right? I'd put nitrogen and hydrogen in a coffee cup collimator and I'd measure what the heat change was, and that would give me the heat of formation of nitrogen dioxide. So it's the same thing in B, right? For sulfur trioxide, it's 3/2 of a mole of oxygen reacting with 1 mole of sulfur to make 1 mole of sulfur trioxide, right? So the 2's cancel there, and I get 3 oxygens going in. 1 sulfur going in to make 1 mole of sulfur trioxide. Again, these are in moles. This is why I'm allowed to do the half thing. Whenever you're doing thermochemical equations, you treat it as moles, not individual atoms. So half a mole of nitrogen, 3/2 of a mole of oxygen, perfectly legal. 1 mole of sodium reacting with half a mole of bromine is going to make 1 mole of sodium bromide. Again, the elements are defined as having no heats of formation. So when I react them together, the heat change represents the heat change in the formation of the compound. And this is where I get heats of formation. They're measured. All right, the other way to implement Hess's law is to look up on a chart. Look up on a chart the heats of formation of the reactants and the products and get the difference between them. So when I have aluminum reacting with iron 3 oxide to form aluminum 3 oxide and iron, all right, and the reaction, a thermite reaction, which is really exothermic. I look them up. I look up the heats of formation of aluminum, and I look up the heats of formation of aluminum oxide, iron 3 oxide, and iron, and I plug in to the sum of the products minus the sum of the reactants to get the change. So you got to go to an appendix and look it up. Aluminum elemental aluminum is 0. Iron 3 oxide is negative 1,669.8. So I look up iron 3 oxide, and I plug it into products minus reactants to get the change. All right, so exothermic reaction. So on the same thing, we're doing the same thing with problem 73, except we're doing it with different reactions. So I look up in the appendix what the heats of formation for oxygen and sulfur dioxide are, and then I subtract it from the heat of formation of sulfur trioxide. So again, the coefficients here matter, right? So you're not making 1 mole of sulfur trioxide, you're making 2. So multiply its heat of formation by 2, that's the sum of the products, and then subtract from that 2 times the heat of formation of sulfur dioxide, plus, not minus, let's change that, plus the heat of formation of oxygen. And get the change. Magnesium hydroxide solid turning into magnesium oxide solid in water. I look up the heats of formation of the products and add them together. I look up the heats of formation of the reactants and then subtract the sum of the reactants from the sum of the products to get the change. Again, exothermic reaction. I look up the heats of formation of nitrogen and water. I multiply the heat of formation of water by gaseous water by 4. Nitrogen 0. Look up the heat of formation for dinitrogen tetraoxide and plug it into products minus reactants to get the change. Again, exothermic reaction. Look up the heats of formation of the products, right? Silicon dioxide and hydrogen chloride gas. Plug it into the sum of the products. Oh, multiply by 4. 4. Multiplied by 4 times 1. Okay, that looks good. Let's get back here. So times 4. Plus the heat of formation for silicon dioxide, and subtract from that the sum of the reactants to get the change. And that's thermochemistry, right? Applying Hess's law by manipulating equations, adding up, plugging into products minus reactants to get the change, measuring heat changes using Q is equal to NC delta T.